Challenges in matching models to observations of gap opening in disks. So I'm well aware that I'm standing between you and wine. Do my best to at least keep it interesting. All right. So we've been talking about a lot of theory so far, and now I want to put in a little bit of an observational perspective. I am a theorist at heart, but I do believe that it is really important for us to be grounded in models. In the observations. So I came in on a red eye this morning, just for the record. So we need to be grounded in the observations because that's really the ground truth here. So here's a suite of some beautifully imaged disks, protoplanetary disks from a paper by Grady et al. There's some. I'm going to be talking a little bit about AB Auriga up here, but you can see that in a lot of these disks, there's evidence of structure, gaps forming, spiral arms, etc. And we've seen this already, but ALMA has also imaged a lot of beautiful disks with structure, more spiral arms, gaps, and rings. And as astronomers, when we look at these things, our response is often something like this. I'm not saying it's planets, but it's planets, because we really want these to have planets, because that would be an indication of how planets form and would inform us about the planet formation process. Okay, so the motivation for this talk is to look at forward modeling of disk structure, and then calculating radiative transfer on those disk structures to predict observables that we can then compare to actual observations of disks. So we see gaps are opened by planets. This is just an image of some hydrodynamic simulations of gap opening by planets. You run these simulations, gaps open. We see them in simulations. They must be happening when planets form in disks. What I work on is looking at radiative transfer on these disks. And so you might imagine that you have your star here, you have your flared disk here. Here's the surface of the disk. It's quite exaggerated to show the flaring of the disk surface. The starlight is incident on the disk surface here, and I'm going to zoom in on a region like this. Okay, and so now here's that region of the disk surface. Here's the stellar light coming incident on it. There's a 1/r² dependence because you have an inverse square law of the stellar radiation. And it's basically absorbed, so to speak, absorbed or scattered at the tau equals 2/3 surface, so roughly order unity in optical depth. And some fraction of this light is absorbed and thermally reprocessed, setting the structure of the disk. And so in protoplanetary disks, this is the primary heat source for the disk. So it's really important for disk structure. And then there's some fraction that just gets scattered and observed directly by an observer. So in my models, I basically model the thermal emission as well as the scattered light. And so based on the thermal structure of the disk, you can integrate along the line of sight to see what the thermally processed radiation looks like. And then to keep in mind is that because of the nature of the dust in the disk, at shorter wavelengths, you have higher opacities. And so when you look in optical near-infrared wavelengths, you're only probing the surface of the disk. And when you go to longer wavelengths, you're able to probe deeper into the disk and perhaps even to the midplane of the disk. So here are some simulated images of an unperturbed disk. And because I'm a theorist, I make up wavelengths, right? And so we have 1, 3, 10, 30, 100, 300, 1,000 angstroms, right? But of course, to an observer, like, why are you making an image of a 30 micron disk? We're never going to be able to do that. So let's focus in on the 1 micron image and the 1 millimeter image. Okay? And so when you're looking at 1 micron, you're looking just at the scattered light from the surface of the disk. Okay, so this is near-infrared scattered light. When you look at 1 millimeter emission, you're looking at thermal emission, and the disk is now becoming optically thin, and you're able to see all the way through to the midplane. And so this is what you might see from large ground-based telescopes or from HST. This is what you would be seeing from ALMA. Okay, so we have this light from the star, illuminating the surface of the disk. Okay, and as I mentioned before, the stellar light sets the temperature structure of the disk. Now, when you open a gap in the disk, you create a shadow. Okay, so there's a shadow now in the trough of the gap, and the far wall is now exposed and illuminated. Okay, the analogy I like to make of this is that you see this crater on the moon, and you can see that part of it is in shadow, and part of it is illuminated and brightened. And you can tell from this image that the geometry of this is such that the sun is to the left, illuminating the crater here, and so the shadowed side is closer to the star, and the brightened side is further away, as I've shown here. Now, this crater on the moon is solid, and so while you might get heating and cooling in here, it's not going to change the shape of the crater. But this is a disk of gas, so it's going to have a thermal response. The area in shadow is going to cool and contract. The area that's brightened is going to heat and expand. And so in the models that I run, I calculate them iteratively to calculate this structure in a self-consistent way. Okay, and so if I take these disks and put in an axisymmetric disk, axisymmetric gap equivalent to, in this case, a 70 Earth mass planet and a 200 Earth mass planet. These are planets at 10 AU, and this top row are 1 micron scattered light images. This bottom row are 1 millimeter thermal emission images. And so you can see, again, at 1 micron, you're seeing light scattered from the surface, and you can see the shadow created by the gap. But if you look at the far edge of the gap, it's been brightened beyond the unperturbed emission you see in a gapless disk. And that effect is increased still more as you increase the mass of the planet and opens a wider and deeper gap. And now, when you look in the 1 millimeter emission, you can see the effect on the thermal structure of the disk. So what you're picking up here, it's not just a change in density due to the opening of the gap. It's also actual cooling in the trough of the gap and then heating on the far side. Okay, because if there hadn't been this heating on the far side, it would basically be, just taking this disk and cutting out a ring from it, but you see the heating due to the brightening of this far side in these images. Okay. Now, we aren't fortunate enough to get disks that are perfectly face on to us most of the time. And so you can look at what happens when you incline these disks. And this is important because when you're looking at 1 millimeter images, these disks more or less keep their symmetry because you're seeing all the way through them. They're optically thin, right? And so if you look at the top-bottom symmetry, they're pretty much symmetric. But when you look at the scattered light, it looks like you're looking down into a bowl. There was a speaker this morning who mentioned this. You get basically the center, where the star would be right here in the center, it is now offset with respect to an ellipse traced out by this bright emission here. Okay. And then another point I want to make is that when you look in polarized scattered light, so polarized scattered light is often used in getting images of protoplanetary disks because light that is basically directly from the star is going to be unpolarized. But if you have light that is scattered off the disk in more or less a perpendicular fashion, that's going to be linearly polarized according to Rayleigh scattering theory. Okay, and so it actually changes the shape of the emission to somewhat. So, for example, here, if you look in this disk here without any planet in it whatsoever, okay. So if we were to trace these lines are isophotes, so lines of constant brightness, and if you trace out those same isophotes here in the polarized image, this disk actually looks like it's tilted a lot more than it actually is. And the reason for that is the fractional polarization. And so this near edge and far edge have less polarization than these wings off to the side, which are closer to 90 degrees angle of scattering. And so that also affects your images when you have a gap in the disk as well. And so going back to this suite of images that I showed you before, these are all polarized scattered light. Okay, and so I want to tell you a little story about AB Auriga. So back in 2018, Oppenheimer et al. Put out a paper looking at a polarized scattered light image of AB Auriga. Okay, it's got it's a Herbig AE star. It's got a beautiful disk around it, not quite face on. And they zoomed in this one section here and changed the contrast here and said there's a little red spot in there. 2.8 sigma, they said, if this spot is real, it corresponds to emission from a hot 5 to 37 Jupiter mass planet. And so I looked at that and squinted real hard and ran some models of what would happen if you put a planet in there and just assume that the planet just pinched the disk in the vertical direction. Okay? And so if you have no planet whatsoever, this is what it would look like. Here's if you put a Saturn mass planet right there, a Jupiter mass planet, and a 3 times Jupiter mass planet. And here's the data. And so, you can, again, trace out an isophote. So this is a line of a contour of constant brightness here. And that seems to match the contour that you see in this 3 Jupiter mass planet scenario. But if you look at the brightness in here, it doesn't match it at all, right? You would expect to see a deep dimple, so to speak, in the disk. And so what you can do is you can take a line through that point and look at the radial surface brightness profile. And you get something that looks like this. These points are the data. No planet is this solid line here. Saturn mass planet is a dotted line in there. And then these other ones are for the Jupiter mass and 3 Jupiter mass planet. And you can clearly see that a 3 Jupiter mass planet does not fit this at all. Okay, maybe you could hide a Jupiter mass planet in it. Here are my reduced chi-squares. So I would argue that the Jupiter is ruled out. But whatever, regardless, a 5 to 37 Jupiter mass planet cannot be hiding in that little dimple. Okay, so that little spot they saw there, 2.8 sigma, probably just spurious. However, this divot that they saw in here is real. Okay, so this is the data from Oppenheimer et al., and this is from a paper by Marshall Perrin and collaborators. And so here is a Subaru ground-based image of AB Auriga. This is total intensity. Okay, and then these 3 panels here are all HST images at 1 micron, 2 micron, and then this is 2 micron polarized light. And so if you look in polarized scattered light, you recover this little dimple. But you don't see it at all in any of these total intensity images at the top. What this plot is showing here is now if you take this so-called P image here and divide it by this image here. So now you're looking at fractional polarization. And you can see that the near side and the far side of the disk have less polarization fraction. And you see these wings where you have increased polarization fractions. So this is just simply a geometric effect due to the fact that you're looking at polarized scattered light. So the moral of this story is that you have to be careful when you're interpreting P images. A lot of these observers who take these beautiful images of protoplanetary disks like to point out all sorts of features in them. You got to take that with a grain of salt. And this is I just want to go through really quickly, what exactly is going on here. So this is, your Rayleigh scattering law in terms of the fractional polarization. If you have light scattering at 90 degrees, you get the maximum amount of polarization. If it's exactly forward scattering or exactly back scattering, you get the least amount. So this is just, the theoretical Rayleigh scattering law. And so what's going on in this disk? And right for this image, I'm just looking at what's going on at the near side and the far side of the disk. Okay, so here's my disk. The observer is off this way. So just bear with me a little bit. I'm going to go through the calculation of the scattering angles. Okay, so this disk is inclined at some angle I. Okay, and this point here is basically analogous to this point here, right? They're equidistant from the star here. But if you calculate the scattering angle, so that's basically this angle here and this angle here, you do the geometry, go back to your high school geometry and calculate your parallel angles and all that. All right, so this angle up here is pi over 2 minus beta, and so beta now is this opening angle of the disk plus I, the inclination. This angle is pi over 2 minus beta minus I. And since beta and I are both positive numbers, this angle is further from 90 degrees than this one. So you have less fractional polarization on this side than that side. And so if you have a polarized scattered light image and the total intensity, you can calculate the polarization fraction, you can figure out which side is the near side and far side of the disk. Okay, and here's that's what you're seeing here. Okay, here's this disk, and this is just without any sort of gap in it whatsoever. Here's the near side of the disk, here's the far side of the disk, and you can see that the fractional polarization is less on the near side than the far side. And so basically, this pattern here is exactly what we're seeing in this model image here. The other story I want to tell you is about HT 163296. So this was imaged with ALMA. This particular image is from the Acela et al. Paper from 2016. And so they see gaps at 50 AU, 80 AU, and 130 AU. Okay, and so this is just a different color scale of that same image. And what I'm going to do is I'm going to overlay now a scattered polarized light image on it, registered to the same position of the star. And so this is imaged by GPI, by Monnier and collaborators. I'm just going to go back and forth a little bit. So here's the ALMA image. You can see this ring here. I want you to focus in on that ring. And then notice that there's this ring here. But they're offset a little bit. Okay, so I'm going to draw in a little ellipse to draw your eye. So this is following the GPI scattered polarized light emission. I'm going to switch back to the ALMA image. There's a clear offset between those two rings. Okay, so what's going on here? So this is one of the images that I showed you before, looking at a gap in a disk. And now I'm tracing out basically the bright ring that you see in these images. And I'm going to switch it to the 1 millimeter corresponding image. And again, if you look at the bright emission here in 1 millimeter, it is offset from that yellow ellipse here. Again, this is just a geometric effect. And so here's my little animation explaining what's going on. So imagine you have a cylinder, all right? This is the near side of the cylinder. This is the far side. So it's like a can of tuna or a cat food can, what have you, all right? And here's the midplane, okay? And I'm going to draw lines, drawing your eye to the midplane. Here's my star, right? And so if I look at the midplane, okay, that's centered on the star. But if I look at the top edge of the can, that's offset. Okay, that's exactly what's going on. In 1 micron, we're seeing just this top edge. In 1 millimeter, we're seeing through to the midplane. Okay, and so, if we compare this image of a gap at 50 AU to my model image, we can see now that the near side of the disk has to be this edge here, and this is the far side. Okay, and then here's the ALMA image compared to my 1 millimeter image. So HD 163296 was also imaged in that D-sharp survey that we've been talking about, and here's the image there. Okay, and so here's the 2016 image. Here's the updated image. And what we see is that these rings look a lot more confined than what we're seeing here. So what we're probably seeing is the migration of millimeter-sized grains being confined in pressure maxima, right? So that's being shepherded into the pressure maxima. And the models that I run have well-mixed dust, okay? So clearly there's a need for improved models here, and this is a project that I'm working on with my collaborator Neil Turner, and yeah, so this is the sort of thing that keeps us theorists in business, right? Oh, look, more complicated data. Let's go work on it. And I just want to end with an advertisement for W first, because we've been seeing, how much ALMA has been doing for imaging disks at 1 millimeter. But I hope you've taken the point that multi-wavelength images are really key to interpreting disk structure. And so W first is one of the instruments on it is going to be a chronographic instrument. And its primary goal is to image exoplanets, to directly image exoplanets, specifically radial velocity planets. So it's a technology demonstration instrument, and it's projected to be 100 to 1,000 times better than any current telescope. And it's meant to be a pathfinder for future missions like HabEx and LUVOIR. Now, so here's some of the exoplanet science themes. So they're going to try to image different kinds of planets, but since we're talking about planet formation, I'm going to focus on the disk science themes, because if you can image exoplanets, you can image disks. And I would argue, in fact, that disks represent the guaranteed science return for the W1st coronagraph, because we know that disks exist around other stars. We've seen this image before. This is HR 4796A. This is a artist conception. But yeah, so disks represent a guaranteed science return for the CGI instrument. And one of the problems is that if there are a significant asteroid or Kuiper belt around exoplanet host stars, we're going to see those disks rather than the planets. So this is why it's great that we're all studying disks, because we'll be able to look at these disks and understand more about planet formation. So here's just a plot showing the sensitivity of various different ground-based and future instruments. So we have Magellan here, HST, GPI, here's STIS, here's where JWST will be. And so these are basically current and near future instruments. They're sensitivities to various different exoplanets. And all these points up here are known directly imaged exoplanets. And W first is going to be operating down here, and here's where we expect radial velocity planets to be showing up. Okay. The equivalent plot for disks looks something like this. And so if you were to take, for instance, TW Hydra and put it at 10 AU, it'll be pretty bright. And this is a STIS and ACS would be able to image down to a few AU in TW Hydra if it were at 10 AU. We are able to image TW Hydra with these instruments, but because it's at 50 AU, we can't probe down quite so close to the star. But again, W first is going to operate down here, and we ought to be able to see 50 Zodi, so basically 50 times the asteroid belt around a star at 10 parsecs from us. So just to summarize, different disk features are revealed at different wavelengths. And so if you look at near-infrared scattered light, you're looking at just surface features. In the sub-millimeter to millimeter, you're seeing continuum thermal emission, primarily from millimeter-size dust grains. And there you're seeing mid-plane features. And if you're looking in scattered polarized light, be careful. Multi-wavelength observations give a more complete picture of disks. ALMA has been great for imaging disks, and W first is also going to be great. So with that, I will take any questions.
So maybe you already explained this, but why was there a little divot? I mean, I thought you ruled out certain masses for the planet.
That's because that was an old paper.
Okay.
So yeah, so so I didn't mention that. If you did have a planet that massive, as massive as those observers were claiming, you would open a gap, right? So that's the other evidence that there isn't a planet that massive in AB Auriga. Yeah.
Have a gap that is illuminated by the star, and for theories to count process Jansky per arc second squared. So what is the physical change in the disk, especially the outer edge, in terms of, I think it's scale heights or
Oh, the scale heights. It's pretty modest. So the heating is more related to the angle of incidence at the surface of the disk. So it doesn't puff up by, like, a factor of 2 or anything. It'll puff up by a few percent, but it's enough to change that angle of incidence so that you get enhanced illumination. So it's all about the angles of incidence at the surface of the disk.
Can you think of an application where, when you want to interpret an ALMA image, it's useful to know which is the near side and which is the far side?
Yeah, because you can get rotational profiles of these disks, right? And so it can be useful in that sense, because if you can tell which way it's rotating, that can be helpful, because you can see which side is receding, which side is coming towards us, right?
From polarization, you're knowing whether you're looking for that or
Exactly,
that.
exactly.
And I just wondered, in terms of looking at something which is basically mid-plane emission, whether there's anything useful in terms of interpreting any of the structures that you gain from which way you're looking at it. I can't think of it, but I just
Right.
wondered if you
There,
thought of.
there was a paper on HD 163296 where they looked at the Keplerian profile of the disk with the ALMA data. I think it was with the Cella 2016 data. And they saw a kink in the radial velocity, which they attributed to a planet perturbing the disk and basically accretion onto a circumplanetary disk. So there, from the velocity information, you can get interesting things.
More about the geometry would be helpful.
Exactly, yeah. Mm-hmm.
Line, can you use the fact that you can image sort of the surface of the disk and the midplane to put interesting constraints on the optical depth or opacities that are giving rise to the optical depth in these disks?
Yeah, I mean, you can, if nothing else, you can back out the scale height of the disk, right? So you can know where the surface of the disk is and actually measure that. And so that gives you a handle on what the thermal scale height of the disk is. So yeah, I think there's a lot you can learn from that. Yeah, you're basically getting a 3D picture of the disk.